Hello everyone, hear me all right? Okay, let's get started. So, for those of you who don't know me, my name is Adam. I'm originally from England. My family is actually all Polish, so I have relatives near to Łódź. So I've been here many times. So it's good to be back. I'm going to dive right in. I've got a lot of content to cover, so I'm going to talk about distributed systems. What is a distributed system? It essentially is a system where the completion of something meaningful, something known as a business transaction sometimes, involves two computers talking to each other. So given that, who here works with a distributed system? That's almost all of you. All right, so you know what I'm talking about. I spent most of my time working in banking. There's a lot of distribution going on here, and I've made pretty much every mistake there is to be made in the book. So that's why I think I'm qualified to talk to you about making mistakes, because I've made them all. I've spent so much time making mistakes and working with distributed systems that I decided to go and work for a company which specializes in distributed systems. We're a company that makes N-Service Bus. Anyone heard of N-Service Bus? That's a few of you. Okay, that's good. So we do a lot of support. We help customers with architecture. We help them through architectural reviews and workshops and things like that. And we come across so many of these common problems, so many times over and over again. I think it's really important to talk about a few of them. So let's talk about a system. Does anyone's system architecture look like this? One big box. Is anyone honest enough to admit it? I see a few gingerly hands going up. I think most of the systems I've worked with in my career look like this, one big box and one machine, sometimes known as a monolith. Now, when people say to me, how can I speed up my system that looks like this? I usually just say, just buy a big box, right? Just throw hardware at it. It's often the most cost-effective way to make something faster. And that's fine, you can scale up to a certain degree, but at some point you're running a terabyte of RAM and 256 cores and you can't throw any more hardware at it. So you think, okay, let's distribute this thing. Let's put this thing on one machine, let's put that thing on another machine, that thing in a container, whatever. Now that's fine, but now we've got things talking to each other, let's say over HTTP APIs, for instance. They're talking to each other over the network, and that introduces latency. So we have to look at what the cost is of these calls. We're newing up our service. This is no longer an in-memory call. This is a call across the network. And that introduces latency. What is latency? It's a time to get that data from one machine to the other, and the time to get the response back from one machine back to that original machine. But the network's fast, right? It's really fast. And when this is running on your machine, when you've got both things running on your machine, it effectively is zero. That latency is effectively zero. And we kind of assume that when we're writing code, that the latency is effectively zero. But when you start running over the LAN, over the WAN, over the internet, things increase in orders of magnitude at each step. And I'm going to illustrate that by, the thing is that when things are fast, when things are nanoseconds, microseconds, milliseconds, it's all just fast, right? It's all just, that's fast. Don't really have to worry about it. But if you think about these things in relative terms, the picture starts to look a bit different. So what I've done is I'm going to scale up. This is actually not a table that I drew. This is a table that someone else drew. But I'm going to scale up one CPU cycle, which on a 3.7 megahertz processor is about 0.3 nanoseconds, right? Incredibly fast, up to 1 second. Okay, so 1,000. We know what it's like to experience 1 second. If we look at some other operations like level 1 cache access, that's a nanoseconds up to 3 seconds in a scaled level. Level 2 cache access, 9 seconds. Level 3 cache access, getting quite high now, 12 nanoseconds. It's not much, but relatively, it's 36 seconds to one CPU cycle. If you want to access memory, minutes, okay, 120 nanoseconds, but relative to a CPU cycle, we're talking minutes now. An SSD disk, days, right? This because 50 to 150 microseconds is not that much more than a couple of nanoseconds, but relatively seconds to days. Okay, we don't use HDDs much anymore, but now we're now talking up to a year. Now, if we go over the network, right, this is within the same continent. 40 milliseconds is damn fast, right? You wait 40 milliseconds for a web response, that's really quick. But relatively, we're in the order of years now. You want to go across continents? Oops, that's not what I wanted. If you want to go across continents, oh, where's that gone? Oh, yeah, is this latency? What's going what's going on here? Something weird's happening. Okay, there we are. We're back to where we should have been. Right. Okay, you want to go across continents? 8 years. Okay, we're doubling it. If you want to go around the world from San Francisco to Sydney, we're up to the order of decades now. And this is where everything is going well. Okay, when everything is working as it should, this is the case. What about when something goes wrong? Sometimes a TCP packet might not arrive. Why? Because network, right? Bad things happen on the network. Luckily, TCP is clever enough to work out how to do a TCP packet retransmit. But that takes about 1 to 3 seconds, which on our order of magnitude is centuries, okay? 100 to 300 years, where one CPU cycle equals 1 second. A virtualization system reboot, we're up to 400 years. SCSI command timeout, 3 millennia. Okay, hardware virtualization system reboot, physical system reboot. Right, we're in order of millennia here, right? And I'm underlining this because as developers, we're not great at realizing the relative cost of newing up that object to calling that service, right? Anyone here use dependency injection? That's most of you, right? So dependency injection is great. I use it a lot as well. But the thing is, that hides where those remote invocations are. You know, the user says, oh, the system's slow. Well, where is it slow? We've become very, very good at hiding where those remote invocations are, right? You read through that thing, you're taking the dependency on I do something, you do something, and that could be a network call. Anyone here use the cloud? That's at least half of you. Okay, so the idea of the cloud is to have machines on tap, right? You need 1,000 machines, you turn the tap and get 1,000 machines. Or you go to the Azure portal and you move the slider. Now, you can provision machines at that level if you're willing to sacrifice some kind of reliability, some level of reliability. And it's kind of like the difference between pets and cattle, right? Your on-site, on-premises machines are like pets. You give them names, you nurture them, you make sure they're running nicely. Cloud machines, you just turn the tap and get some more. You know, one of your cattle fall over, right? It's like, I'll spin up another machine. So if you're actually working in the cloud, your chance of something going wrong actually goes up. Okay, so it's important to bear that in mind. And the thing is that most of this is backed by physics, right? So cloud providers are making things down here a lot faster, they're making things more reliable, but the time to actually transmit stuff across the network, speed of light is a hard constant. Until we start doing quantum computing, and then we can throw this table out. But that's not something I think is going to be a big thing during the rest of my career, but we'll see. So, looking back at our system, we don't have a lot of network calls here, but we're only just getting started. Anyone remember WCF? Remember that? Yeah, you remember it well. Everything should be a remote contract. Everything should be a service contract, so you can just lift stuff out into services wherever you like. And that's the thing, the literature. Anyone heard of microservices? Right? That sound familiar? The literature tells us to distribute. And very often we can end up with kind of distributed monolith, where you've just got network calls going all over the place. And they're all talking to each other over the network instead of memory, and it's important to look at what happens to throughput in that scenario. So looking at original monolith, what tends to happen is as load increases, throughput tends to go up fairly linearly at first, right? And things are very nice. But it starts to level off at some point due to resource contention. And at some point, things can get really bad, and it can actually end up dropping off completely. Why does this happen? Well, .NET is actually a really good example. So .NET has something called garbage collection. And you have Gen 0, Gen 1, and Gen 2. Gen 2 is for really long-lived objects. And when .NET does a Gen 2 garbage collection, that's a stop the world event, right? All user threads are paused. Only the thread doing the garbage collection is allowed to run, and then all the threads resume. Now that is a real-world problem. This is from a blog post by Mark Gravel, who used to work for Stack Overflow. This is Stack Overflow's throughput graph, or rather it's the latency for web requests. These big spikes are .NET Gen 2 garbage collections, right? So users using Stack Overflow were experiencing delays due to Gen 2 garbage collections, right? Throughput was actually dropping right through the floor, and people were complaining about this. So Stack Overflow did a whole load of work to smooth out these peaks. .NET actually has improved, and there's things like background collection and concurrent collection, that kind of stuff, which smooths out these peaks. But Gen 2 garbage collection still has to take place. So even if you smooth these things out, the cost has to be paid. And if you're wondering where a Gen 2 garbage collection fits into that table, it's the millisecond to second rate, which is years or decades, right? So it's a significant cost. If we then look at the distributed monolith, what happens is at first, throughput tends to go up fairly linearly. The drop-off tends to come sooner, right? And the drop-off down to really bad performance tends to come a lot earlier. That's because we're talking over the network. Things take longer. Objects stay in memory for longer. More Gen 2 garbage collection, and things actually get worse by distributing, right? So this brings us to the first rule of distributed systems: is don't distribute your system, right? Buy that bigger box until you can't buy a bigger box, right? At some point you distribute, but be aware of the cost of distributing that system. This should be done carefully, not just spraying distributed calls all over the system. So that's my first common mistake with distributed systems, is distributing everything. This has to be done selectively. A distributed monolith. So, oh my God, what have we created? This is so difficult to work on. You spend so much time battling with this system rather than delivering a new functionality. Who's ever wanted to rewrite their system? That's most of you. I've wanted to do this many times over my career, right? If only I could rewrite the system. I can rewrite this in 6 months. And this is going to be wonderful this time. I'm going to use all the things I've learned about the old system. And the thing is that what tends to happen is when you're working on this monolith, whether it's distributed or not, as time goes past, at the beginning, you tend to deliver functionality quite quickly. But things start to level off a bit because there's a bugs occasionally, and you might have to move stuff around to deliver new functionality, but you're delivering new functionality. But over time, it can kind of like really start to slow down a lot, right? And I've been in a situation before where it kind of flattens off completely. You look back and you say, when was the last time we delivered a feature? 6 months ago? All that time we've been battling with this and just trying to keep it working. We might have delivered something really small, like a new box on a screen or something. So at some point you say, right, let's stop, right? I want to stop. I want to feature freeze this old system. I want to start on a rewrite. And you persuade the business and they say, yeah, okay, go ahead. And you're ecstatic, right? You're going to do everything brilliantly this time. You're going to make it all lovely, and you're going to use all those new techniques you've read about. So you're going to effectively feature freeze the old system, and you're going to start writing a new system. You're going to bring the new system up to the same level of functionality, and you're going to swap one for the other. The only problem is it doesn't take 6 months, right? Because why? We're generally very bad at estimating up front anyway, and often it's not our fault, right? Because it's difficult to remember the hacks that you put in here and how you're going to recreate them in a new system. It's not documented. You've kind of got to go on Code Safari and remind yourself about all those horrible things you did a year ago. And the thing is, at some point, business people need features, right? Who remembers GDPR, right? So GDPR was a hard requirement. Either you deliver some new features to satisfy GDPR, or we're going out of business. Or we're going to get fined millions of euros, and then we're going out of business anyway. So the business say, stop. We need to stop the rewrite. We need something to do with GDPR. So we're going to feature freeze the new system, and we're going to coax a little bit of functionality out of the old system there, just to satisfy these new requirements. The problem is you're now in a situation where you've got a distributed monolith, you've got your lovely new rewrite. This thing probably does new things as well, right? While you're there, can you just make it do this? Right? I've heard that a lot. So you're under pressure to get the new system running as well. So you think, okay, we're going to run both systems. Users are going to use this for some functionality. They're going to use that for some other functionality. And in the middle, we're going to put an integration layer, which does magic. Okay. These things, this is going to suck, right? Because this sucks. And often it's going to sort of just pass things from one to the other. And this thing here ends up being a kind of whole knot in the middle in a world of its own. And before long, you realize you're spending all your time on that thing. And this whole thing, the old system's bleeding into the new, and this whole thing has become the new distributed monolith, right? After 6 months, you think, you know what? I bet I could rewrite this. All of this. And then the cycle starts again. And I've seen that happen in my career. I can even remember the names of systems where I saw this cycle happen, not even just once or twice, but even 3 times. So it's a difficult thing it's a horrible situation to be in, and it's caused by rewriting everything, right? That's my second common mistake, is rewriting everything, right? Do not try that rewrite, okay? Evolve your system. There's one good reason for doing a rewrite. That's your CV, right? If you want to learn some great new techniques and great new technology, that's fine. But I'll give you a tip. Make sure your exit plan is worked out before you start the rewrite. Right? A good rule of thumb, start interviewing about 2 months in, leave about 3 or 4 months in, and things should be okay. All right, let's look at back at the system. Let's say we've defined these 4 different services: ordering, inventory, billing, and shipping. I like to think about distributed system design in terms of a person walking into a building. Right? So a person walks up to the ordering desk and says, I want this order. Here's my credit card, here's my address, please sort it out. The ordering desk, what they can do is they can get on the phone to inventory, and this is a bit like making an HTTP call, right? You make an HTTP call to inventory and you wait for a response. They might make another HTTP call, i.e. they might pick up another phone to the warehouse. Oh, have you got this in stock? Yes, we have. Put the phone down, cool. They pick up the phone to billing and say, hey, can we charge for this? Can you charge a credit card? They say, yep, they call Stripe or whatever. Then they pick up another phone to shipping and say, well, I've just billed for this order, can you ship it? Shipping get on the phone to a courier. The courier says, yes, we can do it. They put the phone down. They say to billing, yeah, we're good to go. Billing puts the phone down. They say to inventory, yeah, we're good to go. They put the phone down. Inventory puts the phone down to ordering. Ordering says, yeah, we're good to go. You've got your order. It's not the only way of doing it. Ordering could pick up 3 phones, right? But if you can do that in code, you have to spin up 3 HTTP calls and tasks and manage them yourself. But that might be a faster way of doing it. First of all, okay, so what are the problems here? First of all, time, right? So this game of telephone takes time, and all the time the user's standing there at the desk waiting for these phone calls to happen. What if something goes wrong, right? What if inventory says, well, the warehouse, I can't call the warehouse, right? I can't get through to them. So you say, sorry, come back later. I can't get through to the warehouse right now. Can't take your order, right? Come back later. Okay. Who actually comes back later? Right? You go somewhere else. You go to Amazon or something instead. So then you read about queues, right? So you read that queues are backed by disk, right? So when I put something in a queue, it's on disk. We're not going to lose it, right? So that's good. So let's take the order from the customer. Let's put a message in the queue, and let's say right away, everything that's good, like give them back a 200 OK, we've got your order. That message goes out to the 3 services. They call their providers. They say everything's okay. Messages come back to the queue. Messages come back to ordering. And ordering at this point just says, well, okay, the order's been fulfilled. I've already told the user I don't have to do anything. But what if something goes wrong? Okay, what if we can't talk to the warehouse? Well, we could say, oh, well, something's gone wrong. That goes back to ordering, and ordering can say, okay, well, we're going to email the customer and say, sorry, I know we said your order was okay, but sorry, something went wrong, and you might give them a voucher or something, I don't know. But there's a lot of code, so I think, why give up straight away, right? Why not retry? Why not retry a few times immediately? And if you can't get through immediately, what you can do, potentially, is put a message back into the queue, right? And the message comes back, say, 5 seconds later, and you try again. If that doesn't work, you put the message back into the queue for maybe, 5 minutes, right? And when that message comes back after 5 minutes, you might try again. And when it comes back, it eventually works. Or, and then you can say, well, okay, let's go back to the queue. What happens if that doesn't fail, if that keeps failing, right? I keep retrying, I've tried after a minute, I've tried after 3 minutes, I've tried after 5 minutes, it keeps failing. At some point, there's just no point continuing. So you might put a message into an error queue, and then a support person can come along and say, oh, we've got a message in the error queue, this message couldn't be serviced. The support person calls the warehouse says, oh, sorry, I spilt coffee on the server, I'm just rebooting it and cleaning it up. They reboot it, the support person puts the message back into the queue, and everything works. The thing is, that might take time, okay? So it might take a long time to sort this out. How long should ordering wait? Should it wait a day? Should it wait 2 days? The business might say, well, if we don't sort it out in a day, we better tell the user something's wrong. What you can do is when you send this original message to the queue from ordering, you can send another message to come back a day later. And if I haven't heard anything back a day later, you can say, well, something went wrong, and you email the user. That's all great, but there's a lot of infrastructure code to write here. So how do we send messages back to the queue, for instance, to come back 5 minutes later or 10 minutes later or a day later? Some queuing systems will do it for you. So Azure Service Bus, you can say, give me back this message in 5 minutes, and it will just do it. Others don't. So RabbitMQ is a good example. If I put a message into a queue into a RabbitMQ, that message will come back to me immediately because RabbitMQ can't delay it. But RabbitMQ has another feature. It has something called time to live. And what we do here is we create a queue with a time to live of 6 hours, and that means that messages only live in this queue for 6 hours, right? But we don't subscribe to that queue, right? We put the message in the queue and we just leave it there. RabbitMQ, after 6 hours, what we can say is we can exchange that message to another queue. So we can say any message that expires from this queue that's not picked up in 6 hours, exchange it to another queue. That queue we do subscribe to, we get that message back in ordering, and we've simulated a delay of 6 hours. So that's all fine. If you want a delay of 15 seconds, you create a queue with a time to live of 15 seconds. You can create another queue with 30 seconds, another queue with 60, another queue with 120, and you can have lots of different delays. But this is the API that we provide in a service bus, for example. Here you can put anything you like in that time span, right? Or you can be really evil and say random.next, right? Random delay. I don't know if there's a business use case for that, maybe. But we don't want customers coming to us and saying, why is in-service bus creating 30,000 queues in my RabbitMQ broker? Well, it's because you've got 30,000 different delays. You know, use less delays. That's not a great answer. So we need something else. Let's take a simple example, 42 seconds, right? Everyone loves the number 42. Now, we only write 42 as 4 and 2 in base 10, right? Decimal, which we invented because of our fingers. But as computer programmers, we know there are other ways of writing numbers, right? You can write this in binary as 101,010 seconds, right? In base 2, or binary. What we could then do is create a queue with a 32-second time to live, a 16-second time to live, an 8, a 4, and 2, and a 1. We can take our number 42, or 101,010 in binary, write it underneath the queues, and that tells us that we can put this message through the 32-second queue. We can skip the 16 because it's got a 0. We put it through the 8, we skip the 4, we put it through the 2, we skip the 1. And by putting this message through the 32-second queue, the 8-second queue, and the 2-second queue, we've simulated a delay of 42 seconds. And we think that's pretty cool. We haven't seen anyone else doing that, and that's something we invented for Service Bus. Using 6 queues, you can have a maximum delay of, 63 seconds, right? That's not very much, so what we actually do is we create 28 queues. That gives you a maximum delay of 2 to 28 seconds, or that many seconds, or 8.5 years, basically. We think 8.5 years is probably enough for anyone. Why 28 queues? Well, we thought, first of all, 25, because that will give you 1 year, which is probably enough for most people. We didn't like 25 because it's odd, so we said even 26. We said, let's be really, really safe. Let's go to 27. And that's odd, so 28's even, so 28 it is. We think 8.5 years is enough for anyone. If anyone wants more than 8.5 years, we'll release a new version which creates 29, and we'll probably do 30 to make it even. We were thinking about making it 32 because that's a nice number in computing, but that will give you 136 years, which is probably, it'd be nice if someone's still using NService Bus 136 years, but it's a little bit far-fetched. If you want to look into that in much more detail, this is another talk that I give which goes into the whole delaying messages thing in a lot more detail. It's quite interesting. So follow that URL. You can take a photo. If you don't get that now, I'm easy to find on Twitter or X or whatever it's called this month. And I will post the slides on Twitter or X after the talk, so you can grab it from there. All right, so there's a lot of infrastructure to write here, right? This whole delaying of messages, and that doesn't even cover serialization of objects, deserialization of objects, guaranteeing transactions around your messaging and your database and that kind of thing. All of those things in their entirety are called a service bus, right? And as I said, Azure Service Bus is not a service bus, it's just a queue, right? It doesn't do all those things for you, it's very low level. So my third common mistake is building a service bus, right? And it's not just NService Bus that's available. There's things like mass transit, there's Rebus, there's all kinds of things, but it's very tempting to build your own because that's fun, right? Building frameworks is fun. You're kind of specifying it and you're kind of the user and the developer. It's a lot of fun. And then you might open source it one day, but it is very, very costly. So I've seen lots of half-built service buses, homegrown service buses in my time, and they tend to be buggy, tend to be undocumented, and you don't realize when you start off how much work you're actually going to have to do. So that's another common mistake I've seen. Who works with complex systems? Complex systems, most of us, yeah. We like to think we work with complex systems. Simple systems would be boring. I've seen lots of architectures which look like this in my time, probably most of the systems I've worked on, unfortunately, often known as a big ball of mud. And it kind of feels like this when you're working this kind of system. It feels like you're kind of drowning in this big ball of mud. So we have better ideas. We decide to split these things up and have nice service boundaries and nicely defined interfaces. And that all works fine for a while, until one day someone from the business bursts into your workspace and says, I've got a fantastic new idea, right? I reckon we can make loads of money with this new feature. And you sort of think about it and you say, yeah, I can do it, but I kind of need something that's actually currently internal up here, over here, that's not in the public interface. But public interfaces can be changed, right? So what's the problem? Why don't we just make an interface change and make the call? So you decide to go for it, you don't see really any harm. And it might be something really innocuous, like the number of items in stock, right? An integer, or a price, a decimal or a double or whatever. So you make the call, you roll it into production, a couple of weeks later, you're making loads of money from this new feature, and everyone's really happy, right? You've delivered this thing, the business is happy, and you're happy. Sooner or later, they burst into your workspace again with a new feature, and you realize you need to do a similar kind of thing again, and make another call from this service down to this service, for instance. And you can kind of see where I'm going with this, right? So no one sets out to make a mess, right? But, given enough time, 6 months, a year, 12 months, or 18 months, you may end up finding calls happening all over the place. And before you know it, you're in this kind of situation where things are just you're sharing data between all the services. And I've seen this happen so many times. And you're in a kind of distributed big ball of mud scenario. And this is very difficult to work with as well. But why does this happen? Now, when we're modeling things, it's very tempting when a business tells us about customers and products, it's very tempting to get up to a whiteboard and write, draw a box for customers and draw a box for products, right? Because these are tangible things. This is what our brains are hardwired for, right? Tangible things. You tell me about a customer, I draw a box for a customer. You tell me about a product, I draw a box for a product. But if we look inside those things and look at the actual data inside them, another pattern can emerge. So the first name and the last name tend to be related, so we're going to put them in one box down here. The status. Does the status have anything to do with the person's name, right? If their name begins with S, are they a gold customer? No, that's ridiculous, right? So status has nothing to do with a customer's name. I know they're related in this customer entity that you might have in your mind, but the status of the customer has nothing to do with their name, right? You can take advantage of that by putting them in a different box. Then you look at the product and then you think, well, the name and description kind of go together, because if something's called a luxury something, the description tells you why it's luxury and why it costs so much and why you have to buy it. So you might put them in one box down here. And then you look at price, right? What's related to price? Well, the business might tell you, well, the price we charge for a customer is related to their status, right? If they're a gold customer, we charge them X. If they're a silver customer, we charge them Y. So price has something to do with status. So I'm going to put them in the same box down here. Now, what we've got effectively is our nouns, our entities, customer, which is a noun. We've got that spread across two different services. And we've got the product spread across two different services. And intuitively, it sounds counterintuitive because we're not good at visualizing things that way. We think, well, really a customer has to be a box. But if you're spreading your nouns across your services, that means you're unlikely to be using a noun-based approach. Because up here, in order to work out what to charge the customer, you have to look up the price here, you have to look up the status here, maybe do a multiplication, right, and then work out what to charge them. That's one of those arrows going from one service to the other. Or you might have an orchestrator, which looks at both services. But ultimately, you're sharing data between services. Down here, all you have to do is link things together with an ID. So sure, these things can each have a customer ID, which can link them together. But you're not sharing the data between them, just IDs. And similarly with a product service, with the product and the product price down here. So the boxes at the top are nouns. These are more, I don't know, maybe more activity based. You know, is this something to do with marketing? Is this something to do with billing? Is this something to do with like customer management or something? When you look at the data inside the boxes, that's where the model emerged. Now, I haven't gone to that in much detail at all, but if you want to look at that in a lot more detail, there's another talk I give which does talk about that. If you follow this URL, I talk much more about modeling and service boundaries and that kind of thing. Again, I'll give out the slides after the talk if you don't get the URL now. But that is my fourth common mistake, is defining services as nouns, as entities. If you end up with a house service and a road service, you might end up in a mess. Let's look back at our system. Okay, so we've seen that we take the order from the customer. We say 200 OK, we send a message to the queue. What happens if there's no stock? Okay, so everything's working, right? Everything's working fine. You can talk to the warehouse. Warehouse just has no stock. So maybe we should hold off on telling customer 200 OK until we know that there's stock. So then we get the message back from the warehouse to say, yes, we've got stock. We put a message back to the queue. That goes back to ordering. And at that point, we're OK. And we can tell the customer then 200 OK. What if we're retrying here and we're putting messages back in the queue? What if we retry and things go horribly wrong and we have to put a message in the error queue and we have to wait for that support person to come along and call the warehouse and sort things out? What's the user doing all this time? They're waiting, right? This might take hours to sort out. Is the web browser going to wait hours for a response? No, it's going to time out. Right? And they say come back later. So wouldn't it be better to wait? So the thing is, we're basically back to this situation here. We're back to this game of telephone, right? And you're kind of stuck because the business already complained that this was slow. We want to make things fast and reliable, but we don't want to take an order if a product's out of stock. So you're kind of in this kind of like problem here. But it's not a technical problem, right? This is in fact a business problem. Right? This is where your business users can add a lot of value. If you say to your business users, well, we've got this problem that We're trying to use a message queue, but the problem is that if we find out something's out of stock, then we've got a problem because we've already told the customer that it's okay, and oh, what do I do? I try and solve this technically. We always try and solve these things technically. But the business will say to you, it's not a problem, right? Just don't bother checking stock. Tell them it's okay. Tell them we've got it. Pretend we've got it, right? Take negative inventory. You think, what? How can we have -1 of something or -10 of something? I say, yep, that's absolutely fine. It's a common business practice, right? Negative inventory is something we are prepared to take, right? They've just solved it for you by business rules. Take negative inventory. Anyone here into DDD? DDD, so Eric Evans and those kind of people. Yeah, so ubiquitous language, something new has entered your ubiquitous language now. Negative inventory, right? That's a business thing that you now know about. And the thing is, they say things like this because they're business people, right? The first rule of business is take the money. Someone's trying to give you money, take it, right? Don't say, oh, I'm not sure if I... No, take the money, sort it out later. A friend of mine did, he actually enrolled in an MBA once. He dropped out shortly after because he realized that all the MBA was really telling him was that the first rule of business is take the money and the rest is just sorting out the stuff later. So that's the first rule of business, take the money. And we can take advantage of that. And because we've got something new in our ubiquitous language, this thing about negative inventory, we can add some value there. We can say, well, what do we do with negative inventory? And the business might say, well, at the end of the day, we look at how much negative inventory we've got. We try and order more from the supplier. Hopefully that will all work. If the supplier says, sorry, we don't make that thing anymore, we'll send those people who ordered it a sorry email and here's a voucher for your next order with a discount. You sort it out. But the important thing is you've taken their money. And this is where you can add real value for the business. You can send a message to the queue to come back a day later and say, well, let's just sort out the negative inventory now, right? You can actually make your system add that value. So that's my 5th common mistake in distributed systems, is striving for consistency. Right? We try and solve consistency problems technically. They're often things that can be solved very easily by talking to the business. Does anyone here actually work with like an e-commerce site that takes money from people? You do? Okay, a few other hands going up. Right, so you may be spotting a fundamental flaw in what I've been talking about so far. Because if we look at this side of the system, what I've said is we take an order from user, we say 200k immediately, and then we do all this stuff here like billing. Now, I'm sure you know that's not how things work in real life, right? You actually have to get your credit card approved. You actually have to make sure that you can pay for it before we say, yes, okay, here's your order. So one thing I've missed out from the diagram so far is the actual website itself. Now, the website is not a service, right? I talk more about this in the talk that I linked about nouns. The website is a physical deployment boundary. These things on the right are the logical services, and they may consist of components. So within billing, you might have components A, B, C, X, Y, and Z. Call them microservices if you want, I don't care. And they might be running on a server somewhere. What the billing service can also do is it can deploy a component into the website, right? A credit card validator. So when the user comes along and says, I want to order this thing, the credit card validator can make an HTTP call to Stripe or whatever it is, this payment provider. That can come back and say everything's okay. Now we want to put a message onto the queue, right? Because we know that the thing can be paid for. In the same way, ordering might consist of various components that are running on a server somewhere. It can also deploy a component into the website, D, and it is that component that puts the message on the queue. Right? So now we've confirmed that the credit card's good to go, we've put the message on the queue, and now we can give back that 200 OK, and this time it's after credit card validation. Now, at that point, or at some point, the message goes off the queue into billing. Billing may or may not need to contact the payment provider again. This may have been a pre-authorization. Now it confirms the payment or something. It may not need to talk to the payment provider again at all. It might just do some internal invoicing and accounting and that kind of thing. It then says that's done. That goes back to ordering, and ordering gets back messages from the other things, inventory and shipping or whatever else, and it knows the order's good to go. How do you actually do this deployment from one logical boundary into a physical boundary? If you follow this link, this is a talk by a friend of mine called Mauro Servienti, and he talks about how to actually do that in code, right? How to actually separate the physical from the logical and have logical servers deploying things into physical boundaries. And that is my 6th bonus common mistake with the distributed system. It's conflating service boundaries, which are logical, with deployment boundaries, which are physical. Okay, so service boundaries are logical design time concerns around business rules. They encapsulate business rules. Deployment boundaries are technical concerns. Okay, once you separate those two things, you're much less likely to end up in that big ball of mud where you've got services making calls to other services and sharing lots of data. Okay, so that's my 6 common mistakes. I've raced through that content fairly quickly, so before I wrap up, are there any questions? Anyone? No? Okay, good. I guess I've covered everything. So if you want to grab me afterwards, I'll be around for a while, so come and grab me, and I do like talking about these things. I hope you enjoy the rest of the conference. Thank you very much.